This video is about iteration with cycles, where we are going to explore what it is and what are the different mathematical subjects involved with it. What's interesting about this subject is that it's one of the non-trivial things about mathematics that not many people may know about, since it is hidden among the many things there is to learn in math. And yet I find it quite useful to find connection between math subjects like circular arrangement or the set of rational numbers, which I'm going to talk about later. I also recommend the video to those who are exploring the Mandelbrot set and the Julia sets and want to understand a bit more. What do I mean by cycle? A cycle is a kind of set. A set is a group of numbers. They are usually put between brackets, like this. In this case, they are read from left to right. For example, 8165 and 1658. These two sets are considered as identical since they have the same numbers, but they are obviously not in the same order. However, if I put these numbers in cycles, meaning that I connect them in closed shapes with arrows, then what matters is the number that comes after which other number. In both cycles shown, the numbers cycle around between 165 and 8. Therefore, they are the same. Let's express a function f of x and set it to 2x. Now I'm going to repeat the function once more. That makes f of x, also known as f2 of x. That's equal to 2 times 2 times x. I'm iterating the function twice. If I iterate the function 3 times, then that's f3 of x, which is 8x. Here are examples for certain values of x. F of 1 equals 2. F2 of 1 equals 4. F3 of 1 equals 8. F of 3 equals 6. F2 of 3 equals 12. F3 of 3 equals 24. Some functions are also created in such a way that when there are certain values of x, where, for example, f2 of x equal x, then it would create a cycle between x and f of x. I made a video on myself using a graphing calculator to explain this, but I, who is a rather slow talker, I couldn't add it to my subject. So if you want to watch it, click on the link in the subscription below. This is an open necklace. We're going to put a certain number of jewels on it. Let's say 5. Each jewel is either orange or blue. Now I'm asking you, how many possibilities are there? Starting with all jewels that are blue, that's 1. Having the first jewel being the only orange one makes 2 of them. But we know that the second jewel can be orange whether the first jewel is blue or orange. So that's 2 more. We found 4 possibilities. The same thing goes when the third jewel is orange. That makes 4 plus 4, so 8 possibilities. Every time we pay attention to a new jewel, we find twice as many possibilities as before. So with the fourth jewel, that's 2 times 8, so 16. And finally, the last one shows that there are a total of 32 possibilities. 32 is actually 2 times 2 times 2 times 2 times 2, meaning 2 to the 5, while there are 5 jewels on the open necklace. That's because the number of possibilities is 2 to the power of n, such that n is the number of jewels. Now what if I ask you, how many ways are there to attach a certain number of jewels with a closed necklace? Let's say 6. Here are the rules. A necklace can be rotated, meaning that a rotated version of a necklace is considered the same. But a necklace can't be flipped. Imagine that each jewel can be seen in only one side and that the other is covered. This means that a mirror version of the necklace will be different from it. Let's compare attached necklaces with detached necklaces. The first closed necklace is similar to 6 different choices of an open necklace because of the rotation. The second necklace is only similar to 2 different cases of an open necklace because it's actually the same arrangement 3 times and there are 2 jewels each. By only leaving 2 jewels on the necklace, we get no more repetition. Now here is the hard part. We are going to pay attention to necklaces that don't repeat, so that the number of jewels on the necklace corresponds to the number of cases of open necklaces that the closed one is similar to. To get 6 jewels, we need groups of either 1, 2, 3, or 6 jewels. Those 4 numbers are the divisors of 6. Since there are 2 to the power of 6, so 64 choices for the arrangement of jewels on an open necklace, the number of jewels on each different non-repetitive closed necklace corresponding to the number of possible open necklaces you can make from them will add up to 64. Before that, we are going to use this method to find the arrangement for 1, 2, and 3 jewels. The only divisor of 1 is itself. So the number of jewels for each different closed necklace with 1 jewel will be 2 to the power of 1, which is 2. As simple as can be, there are 2 ones that fit in 2, so there are 2 different possibilities which we know of. Let's add it on the equation for 64. Now, up next we have the necklace with 2 jewels on it. 1 and 2 are divisors of 2, meaning that we can repeat a single jewel to get 2 of them. 2 to the power of 2 equals 4 will be the total number of jewels in every different closed necklace with 1 and 2 jewels. We know that there are 2 different necklaces with 1 jewel each, so let's add them up. There is only 2 more left to add up to 4. So there can be only 1 possible necklace with 2 jewels that don't repeat. Let's do the same with 3. 2 to the power of 3 is 8. 1 and 3 are divisors of 3. We add up the single jewels. There's 6 left to make 8. Knowing that 6 divided by 3 is 2, we can make 2 different non-repetitive necklaces with 3 jewels. Now that there are only the necklaces with 6 jewels to take care of, we can use the equation for 64 to figure it out. We subtract 64 by the right side of the equation, then we get 54. Dividing by 54 by 6 gives you 9. There are 9 different circular arrangements for blue and orange jewels that don't repeat. Here are all the different necklaces that we found. After repeating the smaller arrangements of joules, every necklace has exactly 6 joules. These are all the possibilities of circular arrangement of joules of 2 different colors, whether they repeat or not, which is a total of 14. If you think that you are up for the task, find all the numbers of possible circular arrangement for 4, 5, and all the way to 10 joules. Pause the video right by the end of this phrase. These are the numeric equations for 2 to the n, where n goes from 1 to 10. Lowercase p of n is the number of circular arrangements that don't repeat for n joules, and capital P of n is the total number of circular arrangements. As you may notice, when n is prime, all you must do to find p of n is take 2 to the power of n subtracted by 2 divided by n, and with that you're sure to get a whole number, which is a neat thing to the eyes of a mathematician. The next thing that I will talk about will have a lot to see with binary numbers. A binary number is almost exactly a number with digits that we'd usually use with decimals, except that instead of working with base 10, we are working with base 2, with each digit being less than 2 instead of less than 10. They are either 0 or 1. For example, 0.01101 is equal to 1 over 2 to the power of 2 plus 1 over 2 to the power of 3 plus 1 over 2 to the power of 5. That's 13 out of 32. Now let's say that I hide all the digits except the first one, and I ask you to find that number by using arithmetic operations, meaning plus, minus, times, divided. First, we notice that the number starts with a 0, so let's write it down. Now what we want is to see the second digit. We can do this by shifting it to the left. It is done by multiplying the number by 2, just like when we do it by multiplying it by 10 with decimals. The number reveals a 0, so we write it down. Multiplying the number by 2 will make it shift to the left again. With that, we get a 1, but then the 1 will be in the way since doubling the number won't stop it from starting with the same 1. The best way would be to subtract it by 1. Let's note the 1. So the trick is to multiply by 2, note the digit, subtract by 1 whenever the digit is 1. Times 2, you get 1, subtract. Times 2, 0, good. Times 2, 1, subtract. And there is the answer, 0.01101, just like the number we had. The sequence we made of doubling and subtracting depended on how the number is expressed in binary. In other words, that sequence results in an expression that describes the number. Here is the system. Start with any number that can be expressed as a fraction, from 0 to 1, and write it down. Multiply it by 2. If that new number is less than 1, draw a blue arrow. Else, draw an orange arrow and subtract the number by 1. If the number is the same as any other, connect the arrow to that number, else write it and go back to step 2. For example, 3/4. If you multiply it by 2, you get 3/2, which is greater than 1. we have to subtract it to get 1/2 pointed by an orange arrow. Now, multiplying 1/2 by 2 makes 1, which we subtract by 1 and get 0. Doubling 0 gives 0, which is less than 1 and is the same, so we can draw a blue arrow and stop there. Another example would be 1/5. Multiplying it by 2 makes 2/5, and this is less than 1. Doubling 2/5 gives 4/5, and it's still less than 1. 4/5 times 2 equals 8/5, which is greater than 1. The subtraction results in 3/5. If we multiply 3/5, it becomes 6/5. Subtracting it gives you 1/5, which is what we started with. Finishing it gives you a cycle. As you can see, the blue arrow means doubling, while the orange arrow also means doubling, but subtracting by 1 afterwards. When the number is less than 1/2, it points with a blue arrow, else it points with an orange arrow. What we want is to find out what are the conditions that make the number create a cycle. Let's express the number as p0 over q0 such that p and q are both positive integers, q0 is less than p0, and those variables are coprime, meaning that they both only have 1 as a common divisor. In short, we have p0 over q0 as a simplified fraction less than 1. This fraction will either follow a blue arrow and proceed p1 over q1, or the arrow will be orange and pq over q2 will be the next fraction. Whatever the next fraction will be, two variables will have to be coprime as well. Starting with the blue arrow, when p0 over q0 is multiplied by 2, there are two cases. If q0 is even, then q1 will be equal to q0 over 2, so that the next fraction's numerator and denominator are both even numbers. If q0 is odd, then we can multiply p by q and obtain p1 and leaving q1 being equal to q0. Now with the orange arrow, we do like before with the multiplying. Subtracting the fraction by 1 won't affect the denominator q0 in relation with q1, but it will decrease the numerator by its denominator. The only thing that affects the denominator is multiplying the fraction by 2 as long as it is even. All it does is reducing it by half, so there is no way that we can get back to the same denominator. Therefore, there can't be any cycle with the denominator as an even number. If the denominator is odd, then it would be the same for all the set. As for the numerator, it will increase whenever the arrow is blue and will decrease whenever the arrow is orange. Since q is greater than p, 2p minus q is less than p. We will only focus on fractions with odd denominators. Let's give it a try. There's 1/3 that becomes 2/3 and then comes back. There's a cycle of 1/5, 2/5, 4/5, and 3/5. 1/7, 2/7, 4/7, and then you have 3/7, 6/7, and 5/7. Two cycles with the same denominator. As for the ninths, you have 6 fractions that exclude 3 ninths and 6 ninths, since they simplify to 1/3 and 2/3. It's beautiful and all, but how do you make sure to find every single cycle with each number of fractions? A snazzy trick to do so would be to use algebra. Let's say we start with some variable x. Then the next number will be x times 2, either subtracted by 1 or nothing, as if we were subtracting by 0. And then we do either one of these operations over and over again until we get back to the number we started with, x. So the whole thing is equal to x. No matter the operations you do, you will end up with x having the same coefficients. Let's call it a, and subtract it by a constant c. Every time you do either one of these operations, the coefficient will double. And so we can set 2 to the n such that n is the number of operations done, meaning the total number of arrows the cycle would have. By isolating x, we get x equals c over 2 to the power of n minus 1. It means that if you're looking for a cycle with n arrows with n fractions, each fraction has to be able to be expressed with 2 to the power of n minus 1 as the denominator. Let's test this thing out. With n being equal to 1, the denominator will be 2 to the power of 1 minus 1, which is 1. So they make integers. The only possibilities are 1 and 0. 1 that becomes itself with an orange arrow, while 0 become itself but with a blue arrow. With n equals 2, we have an alternation between 1/3 and 2/3. With n being equal to 3, we get 2 different cycles with denominator 7. The numerators are 1, 2, 4, then 6, 5, 3. N being equal to 4. The cycles are, out of 15, 1, 2, 4, and 8, then 14, 13, 11, and 7. But here's the thing. 3, 5, 6, 9, 10, and 12 are missing. Now 5 15ths and 10 15ths each simplify to 1/3 and 2/3, but the rest are actually fifths. If we start with 3 15ths, which simplifies to 1/5, 2/5 go next, 4/5, 3/5, and back to 1/5. So it turns out that having a different denominator doesn't stop the cycle from being of 4 as long as there are new fractions. Notice that I haven't specified that the numerator c has to be co-prime with 2 to the power of n minus 1. As for n being equal to 5, there are 6 cycles of 5 different numbers. All 30 fractions are present. By paying attention, all cycles correspond to all the different non-repetitive circular arrangement that we've seen in the last part. But now each arrangement has a fraction and odd denominator to identify each and every arrow. Now that's amazing. Here are all of the necklaces of 6 jewels that we've seen in the last part. Now here is each cycle that corresponds to them. These are every single fractions with denominator of 2 to the power of 6 minus 1, which is equal to 63. This is what they look like when simplified. This is what the function corresponding to the system that we used look like. This is called 2x minus floor of 2x. It doubles x and then subtracts until the value is less than 1. If x is positive, of course. For more details, watch the second video on the Desmos graphing calculator by clicking the link in the description below. These are the function that has the iteration creating all cycles corresponding to the different circular arrangements depending on the initial value chosen. Each function gets across some kind of a box in gray, a square to be precise. They each enter in their own box by a corner, go from one side to the other twice, and gets out by another corner. The box is placed in such a way that it's symmetrical by the axis of the identity line where y equals x. Here are some examples of functions that don't have these properties. As we've seen, most of the parabolic functions else than x squared minus 2, such as x squared minus 1, don't have the properties of making cycles like this. However, it's the case when we are only using real numbers. Things become different when we use complex numbers. Complex numbers are expressed as a plus bi, such as a and b are variables and I has the property of becoming minus 1 when being squared. I is also known as the imaginary unit. A is the real part while b is the imaginary part. The smallest examples in this case are those two cycles. 1.009 plus 0.325i minus 0.087 plus 0.655i and minus 1.422 minus 0.114i. And the same thing can be done with the imaginary unit of the opposite side. The complex numbers point with blue arrows when the imaginary unit is negative, and they point with the orange arrows when the imaginary unit is positive. By including complex numbers in our cycles, it is indeed possible to find every single circular arrangement using functions like this. This is what the iteration trails look like on the function x squared minus 2 with cycles of 1, 2, 3, and 6. I could be talking about this circular arrangement, iterations, cycles, on and on, since there is so much to discover from what we went through, but I might as well leave that to you. For example, the equations for exponential have a certain similarity to the famous Pascal triangle. Why not find out why? Nothing stops us from using 3 different items for circular arrangements. And, of course, those who want to can keep exploring the Mandelbrot set. Math is like a world where we observe right from our reflection. There's so much going on out there.